Yeah, hi, I'm Praveen. I'm a PhD student here at Fire Protection Engineering. My work is to simulate fire phenomena by modeling differential equations, simulating them numerically in a computer. So we use direct numerical simulations, which is an advanced technique to solve these equations, to solve these phenomena. And our solver is a high-performance solver, so it runs on several processors, and it's very computationally intensive. And we run these in supercomputing clusters in California at the DOE labs in Berkeley. And our solver is has got a number of features built into it, and we can use them to simulate a number of configurations, flow configurations, and set up numerical experiments that are not easy to set up with real experiments. So with this, we can get new insight into these problems, and develop new models, and ultimately help in putting out a fire. So here, okay, this is the first video. This is a flame, and the reactants are coming in from the left and the right. So on the left we have fuel, and on the right we have air. And at the interface you see a flame. At the interface we see a flame, and this can be visualized by these colored regions. So the red region is the hot region, and the blue is the cold region. And as we would expect at the flame location, there is a lot of heat release, and the temperature is high. And see these, the flame is transient, so there is the flow structures are interacting with the flame, and we don't see it clearly in this, but we'll see it in the next clip. So it's coming up shortly. Maybe it's just it'll be there in a moment. So this is in this we see the mixing between fuel and air. So the fuel is coming in from the left and air from the right, and as such we don't see the flame, but we know where the flame is from the previous clip. And these colored regions are pockets of fuel and air, so that are mixing with each other. And you see them moving in. So these are what we call eddies. They're being convected into the domain, and they mix, and they move out in this direction. And, yeah. So these are transient events again. Yeah. And now we look at another configuration here. So this is a wall, and fuel is, and it is basically it doesn't participate in, this is the wall here, and we inject fuel close to the wall and air away from it, and again at the interface we see where the fuel and air mix, we see the flame, and that is shown in black here, and the surrounding regions are this is the temperature plot, where the hot region is close to the flame, and as you go away from it, it becomes colder, and that is again expected, because at the flame we expect material to be hot, and again these wavy, wrinkly structures are from the mixing that is taking place between the reactants, the fuel and air, and also the products. And the next one I show, this is the soot field, the field of soot. So these, the red regions are regions where there is a lot of soot, and the green and blue, there isn't that much soot. And from this plot again, we see that most of the soot is produced near the flame and near the fuel region. So the fuel is close to the wall, and there are some of these locations where the soot manages to escape, and this is what we call soot breakthrough. And in real life situations, we'd see this as a cloud of black smoke, and again, the black is where the reaction occurs. But to summarize, my work is to simulate these flames using numerical techniques. And of course, fire is such a complex phenomenon that there are a variety of things that we can learn about it. And the objective is, of course, to put out a fire. But in so doing, we learn a lot about the physics of it, and there are a bunch of or several fields involved in this, like the computing fields. Or the advancement of computing power helps us to simulate more of these flames, and in a more sophisticated manner. And there's a lot of math, and it is a fascinating field in general.